Hello everybody, this is John Buck back with another array signal processing video. And in this video, I'm going to talk about spatial sampling and considering arrays as a kind of spatial sampling and see how that leads us to a spatial equivalent of the Nyquist theorem. To be a little more detailed, the two main things we'll talk about is one, that having a uniform line array of equally spaced omnidirectional sensors can be thought of as a kind of sampling because we have a continuous field, whether it's electromagnetic field or pressure field, that exists continuously in space, but we're only observing it at discrete locations on this grid of discrete locations. And so that's the sort of the sampling part. And we'll see it has a very direct analogy with the time domain sampling you already know from your signal processing classes. And then the second step is, in fact, that any practical array only has a finite aperture, which means a finite observation interval. And that also has impacts on what we're able to say in it, the same way that in time domain DSP classes or data processing classes, you may have learned things that having a finite length recording of a time signal has limitations on our frequency resolution, our ability to resolve closely spaced frequencies. We'll see there's a similar idea going on because any practical array has a finite aperture. Okay, so I'm going to switch over to the whiteboard and we'll get started. Okay, so the first thing, as we mentioned, is that a uniform line array samples the spatial field f of p and t at locations z equals nd. Again, we're just to remind you, the p vector is our position vector, x, y, z, right? And d is the inter-sensor spacing, the spacing between sensors on our uniform line array. Okay, so first we're going to think of, well, we're going along the z-axis, measuring the field f at by point spaced every d along the axis. So if we switch back to the image we had from our first video on uniform line array, right? Again, we're assuming our uniform line array here is lined up along the z-axis, and that we're sampling at every d. And for now, we're going to pretend it goes on forever, right? So that these things sampled by d go on forever. And again, that we're centered at zero. We'll assume eventually that's centered at zero. If it's going on forever, actually, I guess it doesn't matter. I'm getting ahead of myself. But assume this goes on forever, and by separating the sampling part out from the finite aperture part, by pretending it goes on forever, it lets us isolate what effects we see that are due to the inherent in the sampling, that we're taking this continuous field and only observing it at discrete locations, and what other effects we'll see later are due to the finite aperture. Okay, so if we do this, we can rely on our knowledge of time domain sampling as well. So let me switch back to it, right? And so if we get to a clean page here, when we sample in time, we've seen and we've reviewed in videos, and if you are not familiar or haven't seen that, well, again, I'll try to put a link in the description of this to one of my videos from discrete time, or some of my videos from discrete time, about understanding sampling in the frequency domain. But the key idea, right, is that if I sample in time every capital T seconds, I make copies of in frequency every 2 pi over t, right? And I think of that sampling as multiplying by an impulse train. Right? And the reason, again, if we multiply with this in time by this infinite impulse train spaced every capital T, the Fourier transform says that the resulting Fourier transform, the multiplication in time, creates a convolution in frequency between the original Fourier transform and the Fourier transform of the impulse train is itself another impulse train. And I've been lazy with a couple factors of 2 pi here, but the main idea is the conceptual one for now. Again, where that omega s is the radian sampling frequency, 2 pi over t. Right, so that's mathematically what's going on. Conceptually, what we said is multiplying by an impulse train creates copies. When we convolve with a shifted impulse, right, we create a copy of the thing we're convolving with. So we're creating copies in frequency every 2 pi over t. And this is the first replication step, and it's the fundamental place where things get made discrete in time and therefore periodic in frequency. Well, it turns out the exact same mathematics applies to what we're doing spatially here, right? So we could think of creating a discrete version of the field f by multiplying by an impulse train. So let's set that up, right? I might call that fp of t to be analogous, and I say it's the same as taking my continuous spatial, or fp of z rather, taking my field along the z-axis where I'm focusing my array, or where my array lives, and multiplying the general field by that impulse train. Right, so if I'm again just focusing on what's happening on the z-axis, and again I should mention we're going to assume we're working with narrowband signals when we do this. So fp of z is the original field f of z for the narrowband signal multiplied by this train of impulses, but now they're spaced along the z-axis every d. But basically looking at this, this is just a change of variables, right? The math can't care or doesn't know the difference, right? It's just a change of variables. I replaced the t's by z's and the capital T by little d. So the spatial story in frequency needs to be the same, except instead of omega, we use the wave number, and on the z-axis we call it k sub z, because our array is completely along the z-axis for our uniform line array. So it's basically seeing the projection of the wave number on the z domain, on the z-axis, k sub z. So that the continuous spatial spectrum f of k sub z is being convolved with an impulse train where the impulses are spaced every k sub z of s, and where that is, again, 2 pi over the spacing, 2 pi over d. Okay, so we're going to make these copies, and it's natural to ask the same question we asked in the time domain. When does a uniform line array capture all of the information in a propagating narrowband signal? Okay, so pause for a minute and think about, well, what was the key idea in figuring out the sampling criteria in time domain? We're making these copies of the spectrum. What do we need to be true to be able to recover all the information or capture all the information about the signal of interest? So pause the video and think. Right, the key idea is that the copies of these spectrum need not to overlap with each other. So let's get to a fresh screen and see how that works out for us in the spatial version, and how that leads us to this, what I call the Spatial Nyquist theorem. So our plane wave, k sub z, is omega over c times cos of theta, where theta is the polar angle relative to the positive z-axis, right, the positive z direction. And so we have to ask, well, what is the spatial equivalent of having something band limited, right? We know from time domain, the signal has to be band limited in time to have any chance to be able to sample it without that. One of the lucky places that happens for us is that any band limited time signal is going to have be band limited in spatial frequency as well. And the reason is this formula, the omega over c. If we're saying there's a maximum value of omega, or particularly if we're thinking about a narrowband case where there's a single omega, we can use the fact that cosine is also limited, right? We know that cosine will be between plus and minus 1. So that tells us kz, the magnitude of kz is always going to be, or kz is going to fall between minus omega over c and plus omega over c. We can also rewrite that, right? Because we can write omega as 2 pi f, and then plugging that in, we get 2 pi f over c, but c over f is lambda. So this, right, or as we learned in waves classes, c equals lambda times f. So if I put this in for omega and c, I'm left with the f's canceling out from the numerator and denominator. When I plug in here, I'm left with 2 pi over lambda. Okay, so for a narrowband single frequency plane wave, we can think of kz this way, and this actually helps us get to where we need. So we can draw, like, imagine just drawing a typical spectrum, right? And it doesn't necessarily have to be a triangle, but we do know that the wave numbers at most, the largest it can be, will be between 2 pi over lambda and minus 2 pi over lambda. Right, so when we think about this is the original spectrum in continuous z, what happens when we sample? Well, we said we put a copy of this centered at 2 pi over d, right? Our spatial sampling frequency is 2 pi over d. So let's make that copy. I'll color it green maybe to make it clearly different. So the key idea is that we need these copies not to overlap, so we need to figure out, well, where is this left edge? I need to make sure this left edge here is above the right edge of this. And there's a similar copy at minus 2 pi over d, right? These repeat on and on, but I'm just drawing two of them, that's all I need to figure out the sampling criteria. So that edge is, well, it's centered at 2 pi over d, and then it's minus 2 pi over lambda below that. Right? So if I work with this, that tells me I need to put that in an equation saying that this edge has to be above this so they don't overlap. I'm saying that I need 2 pi over d minus 2 pi over lambda to be more than 2 pi over lambda. Right? So now we just want to solve this for the d and lambda. So moving this 2 pi over lambda to the other side, I get 4 pi over lambda. Now I flip things, and I also flip the inequality and cancel out the pi's. Right? So d has to be less than lambda over 2, which leads to the sort of rule of thumb if you're around people in array processing that you need to have two, and taking that the other way, I need 2 sensors per wavelength. Right? I need at least 2d has to be less than lambda. Right, so that's the first main criteria. So let's go back, and then the second point. So that's and that's sometimes called the Spatial Nyquist theorem, a Spatial Nyquist sampling. If we go back to our outline slide here, right, that's the result of this sampling is what we just saw, the Spatial Nyquist theorem, right, which says to preserve all the information in a narrowband propagating plane wave signal, or a collection of plane wave signals, a narrowband propagating signal, we need to sample spatially where we have at least 2 sensors per wavelength. If the signal is not just narrowband but broadband, we need to have at least 2 sensors per wavelength for the smallest wavelength in the signal, which is the highest frequency. Right? And if we don't meet that criteria, we're going to have spatial aliasing, which is to say signals will look like they're coming from different angles, or at least we won't be able to tell among several angles which the signal is coming from, because the relative delay of the narrowband signal, the phases, could come from more than one angle, and so we won't be able to tell where we are for a narrowband signal. That's the first and main thing for this thing. To go on the second piece, I'll mention it. We're going to get into it in more detail later, but let me scroll up and make some room here. Right, so that's for sampling, just pretending it's infinite. Now, for a finite aperture, it's like equivalent that we've multiplied in z in the space by a rectangle. So, again, from our knowledge of Fourier transforms, if we multiply by in time, we're convolving in frequency. What are we convolving with? We're convolving with the Fourier transform of the window. Well, for a discrete rectangular window, right, it's like we're taking, if I make a picture on the z-axis, right, that I'm multiplying by this window effectively on the z-axis to keep, just for the case of this is our n equal 5 sensors. More generally, this would go, be centered at 0 and go from plus n over c to minus n over c for our odd element array. In general, but a rectangle, the Fourier transform of this discrete rectangle will be a discrete time sinc function. Right, so this turns into a very similar story that the thing, we first make periodic copies, and then we convolve with the sinc function that smears them a bit. Now, the smearing is due to the main lobe of the sinc function spreading them out mostly. So we know the wider things are in time, the narrower the main lobe will be in frequency. And so that will make less smearing. It will become less severe. So that tells us that the wider this rectangle is means the larger the aperture of our array, the better we do at reducing the smearing in wave numbers. We're not going to go through all the details of that today. We're going to talk first about beam patterns and how they relate to this. And then as we talk more, we'll see that we'll build the same stories we saw in DSP, about how the main lobe width controls our resolution, our ability to resolve whether an incoming signal contains just a single angle of arrival or 2 closely spaced ones, is limited by the main lobe width of the sinc function, which itself depends on the aperture. All right, so I'm going to stop this video for here. The main idea, though, is the Spatial Nyquist theorem, that by sampling things every d in space, we're making copies in wave number every 2 pi over d. And to avoid aliasing, we need those copies not to overlap, and we ended up with something that is very directly the analog of the Nyquist theorem from time domain with space, where we're saying we need to sample, at least another way to think of it is that the sampling frequency and wave number needs to be twice the maximum wave number of the signal. Okay, so that's all for now. I'll see you next time.